Hey stats students, this is Mr. Ng going over lesson 2.8, fitting models to curved relationships. What's our learning targets? Learning target number 1, use technology to calculate quadratic models. For curved relationships, then calculate and interpret the residuals using that model. Learning target number 2 is essentially the same thing. We're going to use technology to calculate exponential models. For curved relationships, then calculate and interpret residuals using the model. And learning target number 3, we're going to use our residual plots to determine the most appropriate model. Again, I have underneath those learning targets the lesson example and homework example that focuses on that learning target. So let's do a quick review here. When should we use linear or not linear? Okay, I want you to try review number 1, fill in those 2 blanks when based on the residual plots, and then does the pictures down there, our 3 pictures, 1, 2, and 3, do they have a pattern, yes or no, and should we use linear, yes or no? Go ahead and press pause. Okay, remember, if you have a pattern, then don't use linear. No linear. But, actually, I should do that in red, like a red light. No linear. But if there is no pattern, meaning it's scattered, then you can use linear. So example number 1 here, do you see a pattern? Yes or no? We see no pattern, and should we use a linear? Yes. How about number 2? Do you see a pattern? Well, I see one looks curved, so I see a pattern. Yes. Would linear be a good example here? No. We would have to use a non-linear, which is today's lesson, right? Same thing here, curved. Is there a pattern? Yes, it's a curve. So should we use linear? No. Use some kind of curve model. Okay. So what kind of curve models do we have? So learning target number 1, we're going to use this technology to calculate the quadratic models. Okay. So when the association between the 2 variables is linear, back then we used a least squares regression line. LSRLs to model that relationship. When the association is nonlinear, we use technology to calculate other types of models. In some cases, we can use a quadratic model. To fit a nonlinear association between 2 quantitative variables. A quadratic model has a form of y hat, because it's a predicted. This is standard form of quadratics. So you've been focusing on that for many years in high school, junior high, and the graph of the quadratic, you should know, is a parabola. Like this, right? Okay, so let's just quickly review 2 ways of calculating a quadratic model. Number 1, you could use a statistical applet or app that's given by the book, and you just put in the data and don't use commas, okay? But I've been asking you guys to use a graphing calculator. And so to review, number 1, you're going to enter your data into your list, just pressing Stat and Edit, that is next to your left key, into both list 1 and list 2. Number 2, you want to make sure to turn your diagnostics on by pressing second and then 0. And in your catalog, you're looking for the words diagnostic on. It's alphabetical. And then, number 3, find the equation of the quadratic model. You're going to press Stat, Calc, and then on my iPad here, I'm using that app, and it's number 6 called Quad Reg, and you'll put in list 1, list 2. This is just the frequency, and this is where to store it, so you can actually graph it. And then number 4, graph it, you're going to press second stat plot. Make sure it's on, and the type you're going to have is scatter plot. And then your X list will be L1, and your Y list will be list 2. Okay, next page. Example number 1, football. Here is the data for passing yards and the age for 32 NFL quarterbacks for the 2010 season. Okay, I want you to go ahead and press pause, and I want you to go ahead and insert those 32 quarterbacks. List 1 will be age. Let's write that. X, Y, so list 1, and that'll be list 2. Right? Do you guys see that? List 1, list 2, list 1. So you have a lot of data to input. Go ahead and do that, and then press play when you're done. Alright, so I'm going to go ahead and put that in there. Graph and Calc 83 is the one I've used, and I've gone ahead and pressed Stat, Edit, and then I have under list 1 the ages, and list 2 I have the passing yards. Okay, so what we're going to do now is get a quadratic model. So I first want to exit out of here. You can press second mode, and it brings you out here. And then I ask you to press Stat, Calc, and you're looking for Quadratic Regression. In mine, it's number 6. Be careful that it's not quartic, something to the power 4 and number 8, so number 6. Okay, and the nice thing about this app is it kind of tells you, right? It says X list name, so that would be L1. So I'm going to press second 1, comma, which is above the 7, list 2, so second 2, comma, 1, that's the frequency, and then the last part says reg EU, that's the regression equation, where do you want it? And we want it in Y1, so I'm going to press vars, which is next to the down key, go to Y vars, and I'm going to press Y1, and then I'm going to press enter. Okay, and so from here, it gives me a bunch of those numbers. Okay, it tells me it's in standard form, it tells me the A, B, and C's, which are the coefficients, and it tells you R squared, which is the coefficient determination. All right, let's get that into our notes. So go ahead and create a scatter plot and sketch it. So to do that, you're going to press second Y equals. Okay, and there you can go ahead and just click on the top row there. And the reason why in previous videos I had it where you couldn't see those is because I had it in dark mode. So you want L1, L2 on there, and just go ahead and press done, and then you can just press graph, which is on the top there. Okay, what you're going to have to do is just keep pinching your graphs until you find the data, and then you just kind of want to intuitively kind of get your data in there. So the blue dots represents our data. The X represents the age of the quarterback, and then the Y's, the Y-axis represents the yards. Okay, and they try to squeeze that in there by putting it there. Okay, so let's go ahead and get back to our notes. Let's make a sketch here. So I have age down here in years, and then you have yard passing measured in yards, right? And you're just doing a quick sketch, 42, and then a high of maybe 5,000. And then my data kind of looked like you had a bunch of data over here. And you might have like something like that. Okay? And then you saw that the best one was try to fit it through there. Okay, over here we have y hat equals ax squared plus bx plus c. And then from the graphing calculator, your a value was, you can just round to the tenths, so I have, or hundredths, 2 decimal places is fine, negative 13.65 x squared plus the b value was 835.5x, and then the c value was negative 9,258. Okay. 1C, calculate and interpret the residual for Brett Favre was 41 years old in 2010 and had 2,509 passing yards. So let's go ahead and calculate the predicted, which basically means I'm just going to take this equation right here, and age, x-axis is age, so x equals 41. So I'm going to put in 41 for every x value. And don't forget you're using PEMDAS, the order of operations, which is basically telling you to first do the parentheses and exponents, so you would square this one. Then multiply by negative 13.65, and then multiplication and addition. And when you do that, you will get a predicted value of 2,052 yards. Okay, what does this mean with the graph? So if Brett Favre is 42, let's see, like 2,500 is half. We predict that based on here, you know, maybe my graph's not great, but we kind of predict that he would be somewhere like right there. That's what the graph is supposed to show. Okay, so he's supposed to be right there based on our predicted model, okay? And then now we need to just calculate the residual. Remember, this is regular stats, but we wish we went to AP stats. Actual minus the predicted. So the actual was that he passed 2,500 yards, and the predicted over here was 2,052. And it's okay if it gets a negative score. Basically, he got 457. Now let's go ahead and interpret. So he actually got 2,500. So if you think about that, I'll mark it here in yellow. He was what? Above or below? He was above. So Brett Favre had 457 more passing yards than predicted. Which is pretty good for an old guy. Do you see why it's better that he went over? Because you went in football, you get a lot of passing yards, which means you have a strong arm, you're an accurate quarterback. Shouldn't say accurate, but you can pass a lot based on the Quadratic model. Using x as age. Using x equals age. So what does that mean? In other words, the residual for Brett Favre is 457 yards. What's the real statistical analysis? Good for an old guy. Okay. All right. So if you go back and that graph had a r squared. R squared was something we learned last lesson in 2.7. And we had that sentence frame that we used, right? And just fill it out with blanks. The blank percent of the variation in the blank is accounted for by the, I'm going to write here, quadratic model, because we're not using a least squares regression line anymore, relating blank and blank. And don't forget, we have a percentage there, and this is our response, and this is your explanatory and response. So what can we put in there? Based off of the previous screen that we had for Brett Favre, it was 17.6% of the variation in the passing yards. That's my abbreviation, yards. Accounted for by the quadratic model relating age and passing yards. Okay, so that's... All right, so if you use the applet, the app of the book on the top, and you would have gotten this question, but I don't know how to do that with your graphing calculator, so I'll just write an answer and it's okay. I won't ask you to interpret it, but basically our predictions, let's use a different color. Our predictions of passing yards are typically off by about 802 yards. Remember what standard deviation is. It's a spread away from the measure of center. Okay, go ahead and try this next example about baseball, and then we'll go over that together. All right, let's go over the answers for this baseball one. If you put in list 1 your age, the ages of those baseball players, actually of one of the greatest pitchers, Bob Gibson, and list 2 you put in the whip. The whip is basically the win walks plus hits and innings pitched. So in this case, you would want a lower number. So when you calculate the quadratic model for this one, your answer is going to be a y hat after you put into your calculator commands. I'm not going to show you that. 0.009x squared minus 0.558x plus 9.811. Okay, did that part. Sketch the graph. My graph, just a quick sketch. You're going to have his age and you're going to have his width over there. And let's use this. Just have a bunch of points. Kind of look like that. And of course, we can use a quadratic model for this one. Calculate and interpret the residual for the observation when Bob was 24. So, this was 40. This was around 30, 20. I mean, 20 is a little bit further over. Yeah, that's not a good one. Let's try that one better. And then 30. So basically, where is Bob at 24? Well, our prediction would probably show something around, I don't know. The max was about 1.75 and a low of 0.8. Somewhere around there. Maybe like 1.2. But let's calculate it. So let's get the predicted. I'm going to take his number, and then with x equals 24, I'm going to put in 24 here, and when you calculate it out, you will get a predicted of 1.063, 0.603. And then if you actually get the residual, which is his actual minus the predicted, and this is the predicted, so 1.603, and his actual, you can look at 24, it's right up here. So 1.673. So you have a residual of a positive 0.07. What does this mean? This means that Bob's WHIP, when he was what? When he was 24 years old, was 0.07 greater, because that's positive, than the predicted, by the quadratic model of with x equals h. Okay? All right, let's move on now. That was learning target number 1, quadratics. Let's move on to exponentials. All right, next page here, learning target number 3. Use technology to calculate exponential models for curve relationships, then calculate and interpret the residuals using the model. We can use an exponential model to fit a non-linear association between quantitative variables. An exponential model is a model in the form of y hat equals abx. And the x, make that clear, is an exponent. Okay, so there's a couple things I want you to note. A here is the y-intercept. The b is what, going back to your previous math class, this is called the common ratio. And a couple other facts that I want you to know. If b is greater than 1, then we call that exponential growth. Exponential growth. If b is less than 1, so I don't know, 0.8, then we have something called exponential decay. All right, so calculating exponential model, you can either use, again, the two quantitative variables, but if we were in class, we would use the graphing calculator. Your calculator commands are pretty much the same. The only thing that's different is you're going to use one called exponential reg, and on the iPad app that I'm using, it is under A. So it's pretty much everything is the same. Okay, I'm going to press pause. I'm going to go ahead and input all these numbers, and you should too. All right, I'm about to finish my list, but I wanted to show you guys that the calculator is using scientific notation. So how do you do scientific notation on your graphing calculator? Above the 7, you'll see a comma and then a double E. The double E is helping you with, I don't know what it is, but scientific notation. So I'm going to put in 5 billion. So that would be 5.0. And then I'm going to type second, then comma, and then 9. Basically what it's saying is moving the decimal place 9 times to the right. And then I'll do the same thing with this one. 5.56 second, comma, 9. Okay? All right, now let's get this, let's go over that problem. Let me read it to you. I can always come back here. Gordon Moore, one of the founders of Intel Corporation, predicted in 1965 that the number of transistors on an integrated circuit chip would double every 18 months. This is Moore's law, one way to measure the revolution in computing. 3A, create a scatter plot and sketch it. So let's go ahead and get a scatter plot. I'm going to do the same thing. I'm going to go up to second y equals. I'm just going to click on the top there where it has kind of like a plus sign or in that space. I'm just clicking it. And I want to make sure it says L1 and L2, and you can just move it up and down and press done. Okay, and then you can just press graph, which is on the top left up there. And here is my numbers. Actually, this is wrong. The blue dots are fine. The green one's wrong. Okay, so let's go back. Okay, I'm going back to my home screen, so you can just press second mode, which quits. We're going to press stat, calc, and now I want an exponential reg, so that is letter A in mine. I'm going to go second 1, comma, second 2, which is this list 2, comma, I'm going to put in 1 for frequency, and then where do I want this? I want this stored in y equals. So I'm going to press vars near the down arrow, y vars, and just click y1, and it'll erase what's in there. And of course it crashed. Let's try that again. Stat, calc, exponential reg, L1, comma, 2, comma, 1, comma, vars, y1. Don't crash. There it is. Remember, if you don't get the r squared and the r, you have to do diagnostic on. So now we have all of those numbers. Let's go ahead and write down those numbers. And now that you have written down those numbers, you have them screenshot or something, now you can go back to y equals and recognize that it's already in there. Now I can press graph. Okay, what does this mean? Keep pinching around. I'm trying to get all my numbers in there. And just keep putting my fingers on the top screen and keep going down. It's kind of crazy, but that's what I'm doing. I don't know what you're doing to get them all on the screen. Okay, looks like it stops right there. That's the best picture I got, okay? So the blue dots are what I have as my data, and the green is our prediction, right? What would happen if more says it keeps doing that. So let's go ahead and go here. Let's create a scatter plot. And this was the X list, which was years since 1970. So 0 would be 1970. You have 44 years on there, so you're going to go up to 44. Half that's 22. And I don't know, you can just say six thousands, millions, billions, trillions. So you have 5.59, you have 5 trillion. I'm just going to call that 6 trillion. And then 3 trillion. And if you remember from our graph, eventually those numbers get but our model kind of went faster and higher. Okay. All right, so that's my graph. And then if you write your equation from those numbers in the form of y hat equals ab to the x power, so a value from the screen was 1,277. And my b value is approximately 1.431, and then you have to the x power. So this is my exponential model. Calculate and interpret the residual for the year 2014. So 2014, if you think about it, is just since 1970 is the 44. So basically, that's what you're using it from. Okay, let's get that equation. And the first thing I'm going to do, like we've done before, is I'm just going to calculate the predicted. How do I do that? Well, x equals 44. I'm going to put that into my calculator, or you can use the table of values. Let me show you how to do that with this calculator. You want to do your table set, which is on near the up arrow. So I'm going to press second table. And there it says starts at 0 and goes 0.1. And we can also do ask. So second table, let's see our table. And I'm going to type in 44. And that's my answer. So let's go ahead and write down the answer. $9 trillion, 1 billion. No, not trillions. Sorry, thousands, millions, billion, yeah, trillion. So that's 9 trillion, 1 billion, 912,406 transistors. This is our predicted. Okay, so we need to get the residual, and that's just the actual minus the predicted. So our actual is this number. And if you subtract it by our predicted, which was this number, and you do the math, you will get a negative number, which is okay. Negative 3,441,912, 406. Okay. basically, what does that mean? Let's write it over here. In other words, it has about 3.4 billion less or fewer transistors than expected. Based on the exponential model. Based on the exponential model. Okay, remember, what does it mean that it is fewer? So if you go here, and what we're trying to say is that we are trying to be, the predicted based on that red graph would have been something like way up here. But ours was at, the actual was 5 point something, so something down here. So the difference, this is the negative 3.4 billion. What does that basically mean? Moore's math kind of overestimated. Let's write that, overestimated. What we were going to predict, right? Okay, what is the coefficient interpretation of determination? Well, our R squared value was 0.9829. And we just use that sentence frame from above. And we can just go and erase. What percent do we have here? Remember, this is a decimal, so that would be, move it 2 places, so 98.3. 98.3% of the variation in the Y, which was the number of transistors, accounted for the, not a quadratic, but a exponential model relating what is our X, years since 1970, and our Y, which is the number of transistors. So what does that mean? Our data fits very well with what we just created right here. Okay? All right, let's go on to the next page. What just happened? That always happens. I don't know. Go ahead and put in your calculator, and you try example number 4, and then I'm going to quickly go over that problem. All right, let's go over this next page here. Does health predict wealth? Calculating and using an exponential model. Do healthier countries tend to be wealthier countries? A random sample of 20 countries were obtained from gapminder.org. The income per person in US dollars and the life expectancy at birth years were recorded. Create a scatter plot and sketch it. So there's my X, life expectancy, how long you're going to live, measured in years. And then our Y is income measured in dollars. Okay? And if you look at your life expectancy, I see a max of like around the 80s, right? Maybe like 85. So I'm just going to write 85. And I see a minimum of above the 45s. And then for income, I see a minimum of maybe, I'll count by 5s. I see a max of maybe 45. And those are measured in dollars of thousands. Okay, it means thousands, okay? And my data, if you just do it kind of quickly, kind of looks something like this. And if you graphed it, it may have looked something like this, okay? All right, if you calculated the exponential model, remember it's y hat equals ab to the x power, your a value, you should have gotten 5.5161, b value of 1.076, and then to the x power. Okay, for C, calculate and interpret the residual. So again, you're going to do the predicted, and I'm just going to use this equation. And they want us to use a particular country. They want Mexico. So let's find Mexico. And there is Mexico on my list. So that means x equals 77. So I'm going to put in here 77, right? So basically, when you do that, you will get a predicted of 14,164 is my predicted. Okay, let's now do the residual, which is the actual minus the predicted. So our actual is 1,684 minus the predicted, which was down here at 14,164. So that gives me a negative 2,480. Okay, again, what does this mean? If you based off our model, we have 77. Let's use a different color. Maybe this is like 77, and we expect it to be our predicted is 14,000. We predicted it to be like somewhere like right here. Okay, but our residual is negative. It should have been below. That's the residual, negative. So let's make my graph more accurate. Of course, mine's not drawn scale, but hopefully you're getting the visual idea. This was our predicted, and it is below. Okay, so let's go ahead and interpret that. The annual income per person for Mexico was $2,480. Remember, what does the negative mean? Less than predicted by the exponential model with x equal to life expectancy. Okay? All right, let's go ahead now and try that was learning target number 2, exponential. Learning target number 3, use residuals to determine the appropriate model. In some cases, it's hard to tell if quadratic or an exponential model would be better to use. Decide, look at the residual plots. For both models, and choose a model with a residual plot that has what? The most random scattered. So remember, scattered equals good. Scattered equals good. Let's do this last example together. Example number 5, black gold in North Dakota. Choose a model. Texas is the state that produces the most oil in the United States. But which state is the second largest producer? In 2014, North Dakota produced 397 barrels of oil, making it the second largest producer of oil in the United States. A scatterplot of the annual oil production in million barrels versus year since 2000 for the state of Dakota shows a distinct nonlinear relationship. So that's this one right here. That one in yellow. Okay. An exponential model. How do we know it's exponential? It says there on the side. So this is my exponential. But you have to be careful. It says what? Residuals. So this is our residuals. Okay. And then a quadratic right here. How did I know this one was quadratic? Because it says quadratic residual. Okay, so I have 3 colors, yellow, green, and blue. And it tells you the residual plots for these models are shown below. Based on the residuals, which model is more which model is more appropriate? Okay, so if you kind of do a little bit of sketching, this one kind of looks like I can draw that line, right? This one, if you're trying to connect the dots, you're trying to draw something, I don't know. Does that, we haven't learned, but maybe some of you have been in my math class, that looks like a sine curve. So this one looks like a pattern, and patterns are what? Bad. This one has no pattern, and that's actually, it's scattered, so let's write that, scattered. So this is actually good. So let's write which one of these, because the residual plot, use my pen, because the residual plot for the quadratic, the green one for the quadratic model seems more randomly scattered, the quadratic model is more appropriate for these data than the exponential model. So, how do you know which one to pick? Look at the residuals. If you see a pattern, then it's bad. If you see no pattern and it's scattered, that is good. Go ahead and try number 6, which is putting all of our learning targets together. You do it, and then I'll go over it. All right, so what is my quadratic model? I'm just going to quickly draw a graph. And it's pretty much the same. I guess I can just duplicate it in years. And premium measured in thousands of dollars. Let's read this. Many adults try to protect their families by buying life insurance. The policyholder makes regular payments, or premiums, what they're called, to the insurance company in return for the coverage. When the insured person dies, a payment is made to the designated family members or other beneficiaries. How do insurance companies decide how much to charge for life insurance? They rely on a staff of highly trained actuaries, people with expertise in probability, statistics, and advanced mathematics to determine premiums. If someone wants to buy life insurance, the premium will depend on the type and the amount of policy, as well as the personal characteristics like age, gender, and health status. The table shows a premium in dollars for a 10-year life insurance policy worth $1 million for people of various ages in years. Okay, so I did the quadratic, and this is my graph. So age, years, and this is the premium measured in money, right? And over here if I chose to do a that's what my graph looks like. And then I'm just going to write out the equation once I put it into my calculator. Because this side is the quadratic, I got y hat equals 0.379x squared minus 31.191x plus 674.95. Okay, so if I graph the other one, so I'm just going to say this out loud. I'm going to press stat, calc, it's already in there. I'm going to go to exponential reg. I'm using my regular calculator, which you can't see. So it says that's 0. And I want that stored into y1. And I'm going to press calculate. And it gives me a bunch of numbers. And then I'm going to go to zoom 9. And then, so that last graph, I'm going to guess, right? That's what it's trying to do. And this other one, you know, very similarly, let's see, y equals blah, 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 0.93, yeah. And it looks, they all look pretty similar. Okay, this equation has a y hat of 0.939 1.09 to the x power. Okay, so how do you know which is a more appropriate model? Well, you would have to calculate the residuals. And in the residuals, I'm just going to show you really quickly, again, I don't have it on this calculator, is when you're graphing it, to get yourself a picture, you're going to press second y equals, and then when you click on here, on this calculator, you're going to have to just slide it down to residuals. And what it's going to do is going to give you a graph of the residuals. Okay. All right, so if you want to use a graphing calculator, again, I'm just using under y, the y list, you're going to press second stat, and then you'll see number 7 residuals. So that's how you're going to graph that. So I'm just going to do a quick sketch of the graph. And this is what this one looks like. So that's my residual plots. So my question is, which one looks more scattered? Which one looks more scattered? And again, this one kind of looks like a sine curve, or it just looks like there's a pattern. So this one looks like a pattern, which is what? This one looks like a scattered or no pattern, which is what? Good. So let's write that. Which model is more appropriate? Because the residual plot for the exponential model seems more randomly scattered. And generally has smaller residuals, so maybe closer to this line, right? The exponential model is our winner, is more appropriate than the quadratic model. Okay, so 60, using your chosen model, calculate and interpret the residual for a 65-year-old. Taking this, putting it there. Again, just going to do my predicted. That says predicted. And the x for a 65-year-old, you're just going to take x equals 65. And when you do that, put it in here. So 0.939, 1.09 to the 65th power, you will get a prediction of a premium of $254.32. And then to calculate the residual and interpret it, remember that residual is our AP actual. So a 65-year-old actual is 257. 257. Right? You got that from the top of our chart back up there. Minus 254.32, and this gives me a residual of a positive $2.68. Okay, what does that mean? The premium, what you pay every year for the 65-year-old is $2.68, positive or negative. It was positive, so we would say greater than or more, greater than the expected or predicted than the expected based on the exponential model with x equals age in years. Okay, what does that mean, right? So we predicted that a 65-year-old should have a premium of 257, right? And then that number, positive 2.68, the actual is that person was a little bit older. Maybe they have some pre-existing conditions, right? Maybe they're a little bit overweight, they're obese, maybe they have like some chronic diseases in their family and it's starting to show, so you charge a little bit more for that person, okay? So let's just quickly review what we've done so far. In lesson 2.8, we're going away from linears and we're talking about quadratics, exponentials, and we're using those residual plots to determine which of those curved models should we use. See you guys.